Okay. Hello, everyone. I'm Chen Jiejun. I'm the PhD student supervised by Navi, and I'm working on the RAN intelligent controller specific in FlexRig from Mozart 5G. And thank you for Areza deploying the xApp on the cluster. So I'm going to briefly introduce our xApps environment in the Open RAN Studio. And so this is the comparison for our xApp to compare the other open source. Our xApp framework, which called xApp in here, which is isolated from the near real-time rig platform, which is a little bit different based on the standardized xApp framework, which is implemented by the OSC and the ONOS rig. The difference is our xApp, we provide a E2 star, which also named EP42 interface in here to communicate between the xApp and the near real-time rig. And by the standardized interface in between the rig and xApp, the specification only specify there is only use the near real-time rig API. It doesn't have any standardized interface between rig and the xApp. So like you can see from a figure, the OSC rig, they use the rig management router to communicate between the near real-time rig and the xApp. But from the ONOS rig, they use the gRPC to communicate the rig and the xApp. And the other point is our xApp is loosely coupled with the service model, which means the development process of the xApp can be more simplified and less complexity by processing the data, which is tightly coupled with the service model used by the rig. And the baseline SDK provided by the rig in our xApp framework is a unified C SDK, which can provide a different language to the xApp developer to develop their own xApp. But compared to the other open source rig, they provide the xApp, which is independent SDK, and which means each SDK need to create its own API to communicate with the rig. So in our xApp framework, the CSDK, the generalized CSDK also provide less complexity of the xApp developer. And for the latency, since we use this E42 or E2 star interface, which based on the SCTP connection, it provide it provide a real-time connectivity like the one-way latency can reach the control loop latency can reach lower than 50 microseconds compared to the other rig platform, the xApp. And this is our xApp design, internal design. You can see from the rig to the agent, we compile to the standardized E2 interface, which one rig can connect to multiple E2 nodes, like the deployment by Areza. There are 3 E2 nodes in the cluster. One is the monolithic GNOB, another is the CU, and the third one is DU. And from the xApp to the rig, we use our E42 interface, which is the extension from the E2 interface. So it also is the one-to-N relationship, like the rig to agents, which means there are support multiple xApp to connect to rig to communicate different E2 node. And in the rig we use, there are provide multiple service model the customized service model include the MAC, PDCP, RLC, or GTP, which you can extract each layer's information from a RAN. And we also support the standardized service model, which is KPN, radio control, or CCC. For the multi-language supported, supported by our xApp framework, based on the suite we implement in our CSDK, it can unify the API provided by our FlexRig platform to export the Python and Java or Golang or C++, REST or R, and this API to the xApp developer to develop their own xApp. And for the database supported by our FlexApp, including the SQLite, MySQL, or you can disable the database if you don't need. For the this demo, we will show the report service, which is to collect the data from the RAN. So this is the procedure for the report service. You can see from the left side, this is the procedure defined by the ORAN, and then the right side is we extend the procedure provided by the near real-time rig and xApp. Like the xApps need to set up the EP02 connection first, then later do the subscription to the RAN and get the indication message in here. And for the control service, okay, for the control service here is the xApp is also able to send the control message through after it set up the connection. So this is the introduction for the xApp. So we go back to our xApp terminal to see how to run the interactive xApp. Okay, we back to the terminal in here. So as you see from terminal, there are 3 E2 nodes connected. So we can try to, because this xApp has already init, so it has already set up the connection with EP02. So we can try to send the subscription to which E2 node. First, we take this E2 node as an example. We send to the first E2 node. And we want to use subscribe to the KPN service model. And the subscription time interval for the indication message is 10 milliseconds. Then okay, now you can see the message is sent to the RAN now. So I can try to print the KPN state from this E2 node by giving the index of this E2 node. You can see this is the current E2 node information. To see the updating information, you also can call this function called print KPN state loop by giving number of loop you want to print for this state. You can see the table is keeping updating in here. Yeah. And we need to try to generate some traffic in here to see the downlink throughput and uplink throughput get from the KPN service model is updating in our xApp. Now you can see the first UE got the traffic. It's around the downlink traffic is around 40 megabit per second. It's because there is we try to generate the downlink TCP traffic from the core network to the UE1. So if you try to generate the traffic, yes. Can people can hear? Okay, okay. And if we try to generate the traffic for the UE2 in here, you can see the data for the UE2 also increase updating in here. And we in this xApp, we also provide the graph to see the throughput. Let me try to generate the traffic again. Okay. In here from the graph, you can see the throughput for the downlink is also updated. The TCP downlink is around 36, 35, 40 megabit per second in here. Okay, so to stop this xApp, to stop the indication message we receive, to stop getting the indication message, we call xApp end to send a subscribe delete to the E2 node. So we cannot get any more xApp KPN state in here. And all the function we provide in here, like subscribe service model or xApp init and the print KPN state, we are all write in the Python to package the function provided we package the function by the API providing by the xApp. Yes. Yeah. And we also collect the data in the database at the same time when we running the xApp. So you can see this is all the data stored in the database in here. Since this is only a track for, yes, this is limiting the less 1,000. So if we get more, you can see during, okay, this is during the traffic sending. You can see this data all stored in the database in here. And you also can get more information about the MAC layers status for each UE. Yes.
Okay. So now we will try to show you a little bit the code, how to develop xApps. We will show two samples. The first one will be in the C language and another one will be in the Python one. So it will not be very deep. It will be a high-level overview to understand what are the basic steps to develop an xApp. So as you can see on the left side, we see that there are 5 steps that we need to do. So first step is to init. We need to initialize the state of the xApp. We also need, as a second step, to get the status of the connection of the E2 nodes. After this, we need to subscribe to a service model and set the callback function that will, as a next step, receive the indication message that are coming. So if you remember, the subscription will trigger the indication message to come. So they will arrive in the callback and we can process them. So if you focus on the right, on the picture on the right of the screen, you can see that there is the C code. So there are 2 large functions. There is the main function. There is a main function here, and there is the callback that is defined on the bottom. So here in the main function, first we need to initialize our xApp configuration. So we take the arguments for the xApp. So it is this init fr args command. After this, we need to initialize with this command the xApp, init xApp API. So we have an API with several commands that we can use. So these 2 commands in the C will initialize the state of the xApp. So then we can take the status, the second step, we can take the status of the E2 nodes and of the connected E2 nodes, and then we can prepare the ground for the KPM indication. So we will use the KPM service model. So then we need to subscribe here. This is not so complicated. It's just a for loop for every E2 node. So the only thing that we need to do is to use the report SM xApp API function, and here we specify which E2 node ID we want, what service model we want, what interval we want the indication message to come. For example, do we want them to come in 5 milliseconds, in 10 milliseconds, in 2 milliseconds? And then we give the callback function that is here, where we will parse and process the indication messages. So this is the overview of the xApp. So first you initialize, you get the status of the E2 nodes, you subscribe to the service model, and you receive and process all the indication messages in the callback. So you can see that now in Python, it's exactly the same procedure, but the code is a little bit more simplified because it's Python, and we have simplified the functions. If you see, for example, the init, it's just a ric.init command, and you can initialize the state and the configuration of the xApp. Then you can, again, get the state of the connection of the E2 nodes, and you can subscribe with the report GTP SM. This is for the GTP service model. So again, with the report, you can subscribe giving the E2 node ID, the interval, and the callback function. The only difference in this in Python is that the callback function is defined as a class where the indication messages are coming in the handle method. So here, the int parameter, we can see, we take the indication messages and we can process them, for example, like here, printing the timestamp and the latency. So again, it's the same procedure: init, status, get the status of the E2 node, and subscribe, giving the callback to a service model. And you can receive and process the indication message to do whatever you want in the handle function. So the developer code will be in the handle function here to handle the indication messages that are coming and do whatever they want with them. So this was a very brief overview of how to develop xApp in 2 languages. Now, Koa will describe the machine learning development kit that we plan to develop and give. So this will be very, very useful for machine learning applications. So I would like to let, please, Koa, continue.
Okay, so hi everyone, my name is Koa. I'm working on machine learning dev kit for developing machine learning xApps on top of Open RAN Studio. So not long ago, my professor told me that Open RAN has a machine learning specification. So perhaps I will look into it and develop machine learning xApp. During the process, we have learned several lessons and best practices that we think are also useful for other projects, especially projects that needs to do MLOps in production. So we come up with the idea of developing an MLOps framework specifically designed for Open RAN and call it flex control. So basically, the key philosophy of flex control is that it should be a developer-friendly way to bring ORAN compliant machine learning into production. And toward this philosophy, we solve 2+1 challenges. The first challenge is to bridge the seam-to-real gap, which is inherent in machine learning. Whenever you train your model on one distribution and you test your model on another distribution, also known in the machine learning community as a distribution shift problem. The second challenge is near real-time execution of online machine learning. So which is also known as learning while acting in the machine learning community, where you have to separate your model update process from your model execution process, and your model execution process has to be extremely fast. And the last challenge we have to solve is the challenge that we have to face with our first implementation on Kubeflow ourselves, where we find that Kubeflow is quite complicated and with a lot of overhead just for things up and running. So we think perhaps we solve the last challenge that makes things much, much easier for xApp developers. So at EUCNC this year, we will demo our Flex Control framework, to which the key message was that, the key message will be that implementing MLOps on top of Flex Control is simple as 1, 2, 3. So the first step is that you modify the simulation artifacts we provide to you to your use cases. So at EUCNC, we are in collaboration with a manufacturing company. So our use cases is for factory private networking. And then the second step is that you modify the Python components we also provide to you with the already high performance, but you can modify it in the way you want. And then finally, you deploy a whole MLOps pipeline, which is a single line of code. So on the right is one of our experimental results running on top of Open RAN Studio, where Open RAN Studio helps you repeatedly run differently configured experiments. So the gray bars is the traditional approach, where you build a gene-based simulation for training, and then you run it with coroutines in production. And the purple bars is Flex Control on Open RAN Studio, where you directly train on real system, but in a training environment. And you also test on real system, but in a production environment. So you can see that the control latency is almost 10x. And for the KPI targets missed, it's starting at 1.5x, and then we decrease it further and further. Why? Because the coroutines approach does not update the model; it stays relatively the same. So thanks for your listening. This is done with my part. I will leave.
So I want to summarize here, and then we leave the floor for the questions, is that the benefits of Open RAN Studio is that, as we mentioned before, it helps you across all the steps you need in order to interact with the ORAN compliant ecosystem in terms of development, designing a network, deploying and operating the network, measuring the performance, testing the network, making sure that the vendor interoperability is actually in place, and also analyze and evaluate. So I would say that even the documentation that we actually provide for Open RAN Studio is accessible online through this link, where you can actually get access to the materials, also some training courses, some questions that we have designed, and we have been actually providing that for students, and also some experts in the domain that they wanted to go deeper into this. I want to highlight that the one thing that is very nice with Open RAN Studio is that not only we can learn and also play around with the 4G and 5G, we also could learn from the cloud native perspective and also from the ORAN perspective. So I want to also position Open RAN Studio in a bigger picture. So Open RAN Studio is an integrated turnkey solution that leverages existing packages like the OI packages that we are using to build Open RAN Studio. But if you need something more complex and more flexible, there is also another platform which is called Multi-X Platform Development Kit. So this is the hardware software component, which essentially provides you a multi-vendor environment with the radio frontend. So Open RAN Studio is essentially an emulated end-to-end environment, whereas the PDK is the multi-vendor environment that has also the radio frontend, so you can actually have experimentation in a live network. PDK also includes the Open RAN Studio. So when you have PDK, you also have Open RAN Studio, and the Pro version is really designed for industrial grade network. It is designed for the private 5G for the deployment, which is essentially the next level of the PDK. So with that, I want to give my definition of Open RAN or ORAN v2.0, which essentially I'm adding few new keywords into existing definitions. So one of the keywords that I'm throwing is the cloud native, which is used as a virtualization in the standard ORAN definition. Here, I really want to say we truly need a cloud native an open ecosystem, which you see here, in order to get the most of the agility that we could get from the Kubernetes. And fully interoperable multi-vendor RAN. So multi-vendor, again, as we discussed, is very important, and I see it very relevant when we go to the private network, when the cost become a bottleneck, and you need to also optimize the cost. So you need to mix and match the vendors to correspond to the cost constraint, but as well as the performance constraint. And the fact that the use cases must also consider private network use cases, which so far in the ORAN, the most of the use cases are more related to the public network, the operators network. And all of this empowered by an open ecosystem. And this open ecosystem is because of the definition that we had at the beginning, which means that we need a collective action. Collective action means an open ecosystem where everyone could contribute and benefit. And that is actually one of the ideas of the Open RAN Studio, is to create this open ecosystem. So with that, I want to thank you for joining us today. Now come up with some questions. So now the floor is. Any questions from the people in the?
Hello.
In this, yes.
This is Farhad from CTTC.
Hi.
Do you hear me?
Yes. Yes.
First of all, thank you for this session. And I want to know your point about the relation between RApps and xApps. It is correct to say that xApps is fed by RApps, by AI interface, or what is exactly the relation between RApps and xApps? I ask this question because currently I'm working on my brainchild to somehow enable SMO to provide some RApps services by third party. Thank you.
Okay, thank you very much, Farad, for your question. So this is a topic actually we are working and studying right now too. So what we have seen so far from the standards is that RApps want to utilize A1 interface for three things, as you already know. They want to utilize them for policy enforcement, for enrichment information, and for machine learning, machine learning which is not yet standardized. So what we understand is that the RApps indeed want to utilize the xApps of the near real-time rig, and they want to provide high-level configuration. For example, policy configuration of the xApps to obtain enrichment information from the xApps and train machine learning models and send them to the xApps to deploy them or deploy them in the non-real-time rig in non-real-time. So all these are very relevant questions. So we believe that the RApps will have this responsibility. They will need to find and the appropriate xApps to enforce the policies.
Maybe I can add one thing. The way also I see it is that if you look at the beginning, the way we see is that the near RT rig and xApp belong to the vendors, whereas the non-RT rig and RApps belongs to the operator. So this, I think this is one thing, very important information. From that perspective, xApps are technology dependent, except they know 5G, they know resource block, they know handover, but RApps, they tend to be technology agnostic. So not knowing anything necessarily about the technology, but setting the high level policies, right? Like energy efficiency or performance or a specific, let's say, SLA for a slice or SLA for a particular user. So this is what, but I can maybe, from this is my personal opinion, from what we understood from the specification is still not precise, and it is not matured enough so that it gives us the right information. I would recommend to wait. Even ORAPs are not defined necessarily properly, so this is still a question mark, I would say, for everyone. Thank you. I hope we answered your question.
Thank you very much.
Yeah. Any other questions from the participants?
I have a question. This may not be directly related to xApp development, but from, let's say, from Open RAN deployment perspective, right now, since xApps are not really mature, so the distributed SON features, functionalities, how do you feel is going to be the interconnect between the Open RAN towards the 3GPP SON modules, which are already deployed in the operator network? So,
okay.
Any
I understand. So my understanding is that, so back then we had the ORAN, radio resource management, mobility load balancing functions, and actually self-organized networking, the SON that you were saying, and that was done through a specific protocol interacting with the RRC layer and so forth. So I would see that more and more the self-organized networking, the SON and RRM and all of those will be realized in a form of a xApp. Now, if you ask me how it's going to be split between xApp and ORAP, I don't have a good answer for you. And the interplay between them, you are maybe referring to a conflicts. Maybe we have a deployment that at one point we are using self-organized networking, and at another point we are using Open RAN. So this obviously is a conflict that needs to be managed. If we have, let's say, legacy SON plus the current ORAN architecture, obviously there will be conflict in some decision making, and I don't think we can have both at the same time. Maybe we can have both at the same time for different segments of the network. If the ORAN specification goes forward, I mean, we have RAN control service model, we have a cell configuration and control that is coming. If that goes forward, it might be that we could realize SON using ORAN framework. For instance, in a RAN control service model, we are going to have RB control, radio bearer control, which goes towards the direction that you are saying. I hope we answered your questions. Please complete if there is part of your question that we did not answer.
Thank you, Naveed. This is really a good discussion. But what I was understanding is from connectivity from between SON and Open RAN. Let's say if I do not, because right now there is no xApp maturity. So if an operator wants to deploy Open RAN today, and if he's having a SON legacy SON already installed, and if he wants to leverage those already available applications of modules of SON, can he connect? How he connects? Does he connect via O1? Or does he connect via O1? How does it work towards interfacing?
I would say that already one of the benefits that we already see clearly, I mean, legacy systems, they have their own monitoring system already in place. So there is no discussion about that. But they can already use it from this key performance monitoring part to analyze per user, per slice, per network, status information. So maybe the first step would be just not the control part, but the report part. So the only service, you know that RIG provides 4 services. There is report, control, insert, and policy, right? So obviously the policy, insert, and control will conflict with the legacy system, but the report will not conflict. So probably one migration step would be just to use ORAN, Open RAN for the status monitoring per UE and per slice and per network, while we are going more and more forward towards the ORAN. So I hope I answered part of your question.
Okay, thank you, Navid. It was
You're
very
welcome.
good.
You're welcome.
There are some questions in the chat.
Maybe those that send the questions in the chat, if they want, you can actually also. Okay, Open RAN v2.0 is not a formal term, is my own personal opinion that the original ORAN definition, ORAN is formed by the public operator first, right? So the use cases were more for the public network. And ORAN v2.0 is a definition that I try to promote to say that that definition, while it is good, if you want to go to the private network and to the private and public clouds, we need a better definition. So it is not a let's say a formal definition provided by ORAN. It is our definition, let's put it like that.